Okay, so here's another variant of scheduling job, but now we want to minimize lateness. So what is this variant? Well, the basic idea is that we get the jobs, and every job has, we can schedule it to start at time Si. The duration of the job is Ti, and the finish time of the job is Si plus Ti, naturally, right? We're going to call it Fi. Now, unfortunately, for every job, there is a deadline, Di, right? So the lateness of a job is, of course, the difference between the finish time and the deadline, right? If this quantity is negative, namely you completed the job before the schedule, then there is no lateness, so you take maximum with 0. Right? So this is going to be the lateness of the I job, Li. And we are trying to minimize the maximum. L is going to be the maximum of the latenesses, so we want to minimize this lateness. Okay, now this is something you have to handle every day because you have homeworks and so on, and you have deadlines, and we kind of know what we do in real life, right? In real life, we always handle whatever has the first deadline first, right? It's not the only strategy, and if the deadline is far enough, you might have different strategy, but that's kind of the natural strategy, and it's natural to assume that this is the right strategy, right? So this is one of those problems where we kind of we solve it every day, so there is a natural solution. And that we know, we just need to prove that this is the right strategy. Okay? So there is a specific example here, right? Because we have the time schedule, and we have the jobs. And if we do J3 is 1 unit, so we do it first, right? And we do that, and let's assume that if we do it in this order, then J1 is completed at unit times 8, right? But the deadline for job 1 is 6, so the lateness is going to be 2. Right? Similarly, J5 is going to be completed at time 11, and its deadline is 14, so we completed before the deadline, so the lateness for it is 0. And J4, similarly, the lateness is going to be 6. Okay, so this is this example. And I kind of gave the game away because of what the greedy algorithm is. But let's first, think about other strategies, because depending on the version, there are infinite number of different versions of this problem, right? So depending on the version that you look at, you're going to use the same templated algorithm, but the strategy would be different. Okay, so the scheduler is going to do things like start at the current, it's going to have a current time, and it's going to have max lateness, and then it's going to choose a job from the remaining set of jobs, schedule it, and update the lateness according to what the current lateness of the current job was, right? So this is the basic template of the algorithm. And the nice thing about it is that it's very simple, right? The simplicity here is important because we are looking on a problem where we have n different jobs, so the number of different ordering is exponential and factorial. So it's nice to have a very simple algorithm, especially if it's correct, like in this case. Okay, so the big decision here is deciding how to pick the ith job, right? The next job to handle. And as we said, there is the EDF, which is earliest deadline first, which is the natural strategy in the first one. But another natural strategy, which is natural to do, is shortest job first. Especially if you have faraway deadlines, you really want to get rid of the easy things first. And then there is a third strategy, which is you shortest slack first, right? So you look on a job and you look on its duration and you subtract from the deadline, right? So this is really the deadline when you have to start the job, right? And you want to, you sort according to that. And I don't necessarily, right, so you sort by when you have to start, but yeah, in real life you wouldn't use it because for personal things, because the time we spend on the job is something that usually is fungible, right? You can spend less time on a job if you really have to, and do a lousy job about it. So this is not a very natural strategy. Anyway, why don't you think about counterexamples to the first two strategies, showing that they are not optimal? Okay, so let's prove that EDF is indeed, earliest deadline first, is indeed the optimal strategy. It minimizes lateness. And the proof again is doing the same exchange argument we had seen before. So the first technicality we have to handle, which is kind of a silly technicality, so I'm just going to mention it without spending too much time on it, is look on a schedule and assume that you have gaps, right? Where you're not scheduling anything. This is idle time. Now, human needs idle time, we need vacation time, but computers don't. So clearly, if we have a schedule that is minimizing lateness, we will get even better schedule or no worse schedule, but if we bunch all the job together and just do them one after one, right? So this is this, this is this, and this is this. Right? So this is equivalently good, and it's much more compact. So we can assume that there is no idle time. Completely not true for real life, and doubly so for when you have to do things like homeworks or similar stuff, right? There's always the internet to waste time on. So anyway, but the first lemma claims that there is no idle time. We just argued why this is true. The second thing we want to argue is that there are no inversions, right? So if there is an inversion, what is an inversion? Inversion again is, so in fact this is best drawn on the time. This is the job, let's say J, I, J, J. Those two jobs are scheduled, and then they have their deadlines. This is the one deadline, this is the other deadline, right? And this is a feasible schedule. So assume this is the deadline for the first job, and this is the deadline for the second job, right? So they flip their inversion, right? The first scheduled job, its deadline is later than the second job, right? So this is not very natural, right? Because in the scheduling, it's much more natural to flip it, right? An important thing to observe is that, if I flip them, then in either, their lateness, if it's feasible, then I'm subtracting the, in this case that they do it, both two jobs are before the deadline, so there is nothing to minimize. But if you think about more interesting cases, it's easy to verify that if you have an inversion like that, exchanging the jobs improve things, right? Okay, so now, of course, this is harder to see, so we're going to think about the case that they have two consecutive jobs that are inverted, but that's immediate, this is easy to see that indeed if there are two jobs that are inverted, and you draw it the way I draw it, right? You draw the jobs on one time schedule and the deadline on the other, then if you have inversion, which means that the edge between their end time and their deadline, those segments intersect, then there must be two consecutive ones that intersect. And the proof of that is hopefully immediate, right? As we essentially saw before. Okay, so that's good. So now let's prove the optimality, right? Let's look on an optimal schedule that minimizes the number of inversions. Okay. Again, inversions not necessarily are consecutive, right? Okay. Otherwise, there are two jobs that are inverted, that are consecutives. Okay. So we have two jobs that are consecutive and are inverted, right? So one option is the one I already drew, where the deadlines was to the right of two jobs, and then clearly swapping them doesn't matter, right? So the more interesting case is where it does matter, right? Because one of them is past the deadline, right? So let's assume, for example, we have this situation. This is past the deadline, so you have to pay this difference. This one is not, right? I still claim that this is better to schedule them first, right? Because if I schedule the first one first, right, then maybe I should draw it below. If I flip them, let's make this job a bit longer if you don't mind. The first one is a bit longer. So if I schedule the first one first, I exchange them, right? Then it would go to this job, and then the big job would go here, and it would pay this, right? So it's still, the bigger job is still late, right? But this new interval is smaller than this interval, as one can easily see, right? And the reason is because those two intervals, only I didn't draw it like that, the two intervals end in the same time, but the deadline of this, the second job, moved forward. That's the intuition of what's going on, right? If, yeah. So that's the situation. That's why it works. Okay, so convince yourself that this argument indeed works. I know it's a bit sketchy, but hopefully you can convince yourself it's correct. And as such, EDF is an optimal strategy, and the greedy algorithm works.